Welcome, everyone. Thank you for attending today's SEL webinar, SEL Solutions for Reducing Potential Wildfire Risk. My name is Reagan Lynch. I am an application engineer from Fair Oaks Ranch, Texas. I will be today's moderator. Before we start, I would like to bring a few items to your attention. This is an audio-only broadcast. All participants are muted. Today's webinar will be a 2-hour-long webinar, including questions at the end of the presentation. There will be a recording, which will be available on our website soon. If you have any questions throughout the presentation, please submit them to all the presentation panelists with the Q&A tool at the bottom right-hand corner of the application. Any questions that are not addressed during the live event will be answered by our experts via email. We will also be offering PDH credits for participation in today's live event. To receive PDH credits, you must attend at least 75% of the webinar. No partial credits will be awarded. You will receive a certificate via email. Our presenters today are Anthony Rahimanajad, Jared Candelaria, and Hardesh Khatri. Anthony Rahimanajad is a lead product sales manager at SEL in the Distribution Controls and Sensors Group. He joined SEL in 2015 as an industrial solution engineer and has since held roles as an application engineer and as a sales engineer. Prior to joining SEL, he held a position as a senior power system engineer for Eaton Engineering Services. Anthony received his BSEE degree from North Carolina State University and is a registered professional engineer in the state of North Carolina. Jared Candelaria earned a BSEET from the Metropolitan State University of Denver in 2007 and an MSEE from the University of Colorado at Denver in 2012. Jared joined SEL in 2012 and is currently an application engineer in Lakewood, Colorado. Prior to joining SEL, Jared worked at consulting firms in the Denver area doing substation design, commissioning, and system protection. He is an IEEE member and a registered professional engineer in Colorado and California. Hardesh Khatri received his BE in electrical engineering from NED University of Engineering and Technology, Karachi, in 2012, and his MS in Electric Power Systems Engineering from North Carolina State University in 2015. He was also awarded a graduate certificate in Renewable Electric Energy Systems in 2015. Hardesh joined SEL in 2016 and is currently a protection application engineer. His responsibilities include providing application support and technical training for protective relay users. Hardesh is the registered professional engineer in the state of California, a member of the IEEE and PES, and actively involved in the Power Systems Relaying and Control Committee. I will pass the phone to Anthony, and we will get started.
Thanks, Reagan. And thanks, everyone, for joining us today. So, as he said, my name is Anthony Rahimanajad, and today we have a great agenda for you. We're going to talk about a few different areas related to fire mitigation solutions. We're going to start off talking about downed conductors and the threats they pose for fire ignition, as well as solutions to detecting downed conductors on power distribution systems. Then we're going to go into ground fault as part of this discussion, look at the ground fault detection sensitivity versus system grounding and how this has a large impact on the ability to detect high impedance faults that are caused by downed conductors. We'll talk about ArcSense technology and how this can be applied, and also we will touch on some wildfire mitigation solutions for transmission systems as well. As most of you are probably aware, wildfire mitigation is a growing concern. So we have here the millions of acres burned by wildfires for the United States, and as we can see, this is trending upwards. And as in many parts of the world, last year was the worst fire season on record. So of course, we're looking for solutions to address potential concerns with wildfires. Now, as I mentioned before, downed conductors, when it comes to fires that are ignited by power systems, downed conductors are a significant concern. You know, vegetation contact is one of the largest ignition drivers for power system induced wildfires. And of course, these are they pose a significant public safety risk from a electric shock standpoint, as well as a fire ignition standpoint. Now, before we get too far into looking at solutions for detecting down conductors, let's make sure we're all on the same page about what I mean when I say a down conductor. So a down conductor is most often thought of as a break where we have a break of our conductor and then it's laying on the ground. Now, that is probably the most common condition to having a down conductor, but we can also have conditions where we have, let's say, a broken cross arm or some other damage to our pole or conductor carrying infrastructure that allows our conductor to make contact with the ground or make contact with something that is in contact with the ground while still being connected to downstream load. Now, in this case, let's say we have maybe a tree leaning up against an overhead conductor that has not broken. That is still, for the purposes of our discussion, we're going to still refer to that as a down conductor. And in many cases, a down conductor may result in a high impedance fault. And we're going to talk about high impedance fault at length, but just to be clear, when I'm mentioning a high impedance fault, I'm talking about a fault that is typically less than 100 amps of fault current. And the surface, so multiple conditions will influence, of course, the amount of fault current that we have when we have that we see when we have a high impedance fault. But one of the largest influencers of that is going to be the type of surface that our conductor is making contact with. And you can see here some examples of different surface types and typical available fault currents. And this is actually taken from some stage down conductor testing that was conducted, and there's actually a paper available on our website that talks a little bit more about this. So this gives us an idea of what we mean when we talk about a down conductor and high impedance fault. This is again from another stage test, and we can see that in this high impedance fault we have very little fault current, and it's difficult and practically impossible to pick out this high impedance fault if we're just looking at the total RMS current magnitude back at our substation. So we need, so in many cases, our traditional protection is going to be insufficient. Let's talk about power system grounding and how this has an impact on our protection sensitivity when it comes to ground fault detection and detecting high impedance faults in particular. So looking at what most of the distribution systems in North America are going to be 4-wire multi-grounded systems. Now we have some systems that are, some 3-wire systems and some ungrounded systems, but predominantly we're going to see 4-wire multi-point grounded systems. Now, these systems have high availability of ground fault current because we're solidly grounded. So that is for faults that are not high impedance faults, that is going to allow us to be able to quickly detect and clear those faults. Now, one of the challenges with these types of systems is that most of the time our loads are going to be connected phase to neutral. And so in this case, this allows us to have our equipment only rated for line to neutral voltage. However, is going to introduce the challenge of any imbalance that we see on these systems is going to generate zero sequence current. So this 3IO current. And so here's an example power system. We have a few feeders here. And in this case, we are looking at a potential fault on feeder number 3. Now, on this feeder, we have an imbalance of our loading. So say either our single phase loads are not typically balanced perfectly, or we can also have the case where we have to plan for contingencies of a large single phase outage on a large single phase lateral, right? So say we blow the fuse on a large single phase branch or lateral, and now we have this imbalance. And so we can see this imbalance is going to appear in our zero sequence circuit right here, and that we're going to have standing zero sequence current. Now, the challenge with this is that we can see in this case, and this is in a simulated fault scenario, we're actually introducing a fault on the system actually improves that imbalance. And so when we introduce a high impedance fault, this 200 ohm fault, it actually reduces that residual, that zero sequence current that we're measuring from 20 amps to 18 amps. And the main challenge there is that typically, traditionally, we're going to use that zero sequence current. That is going to be the current that we look at for our fault pickup, okay? And so this is going to be the current we use to operate our ground fault protection in most traditional protection schemes. And so if I have a situation where introducing a high impedance fault actually reduces this, has the potential to reduce this current that I'm using for my fault pickup, then there's really, there's no way I'm going to be able to detect those high impedance faults using this traditional zero sequence based 50-51 elements, so this traditional protection. So I need another method specifically to detect high impedance faults on the power system, because in many cases that, especially on 4-wire multi-point grounded systems, that whatever our standing imbalance is, or whatever the worst case standing imbalance, that dictates the sensitivity of our ground fault pickup, because we have, for traditional protection, because we have to make sure that we set it above that so that we don't have a nuisance trip. So how can we detect these? We need, as mentioned before, we need a dedicated element to detect high impedance fault. And so that is where SEL ArcSense technology comes in. And AST is designed to specifically detect the arcing that is associated with a high impedance fault. In most cases, when you have a high impedance fault, you're going to have intermittent arcing in that fault. And that arcing is very rich in harmonic content. So we're going to actually look at the harmonic content of the measured current and use that information in order to detect high impedance faults in the system. And the way that we're doing this is we're using what's called a sum of difference currents. And this is taking, essentially, we're taking the time slotted currents. We're doing 32 samples per cycle, and we're going to subtract, the sample that we take now from the sample one cycle ago, and then we're going to sum all of those differences together. So a sum of difference. And what you get from this is this frequency response. We're adding some gain here, and we're ending up with this overall frequency response for the sum of difference currents, that is the input into our AST algorithm. Now, one thing that you'll notice here that's very interesting is we're filtering out DC, and we're filtering out all of our integer harmonics, okay? We're looking for the current contact. We're looking for the stuff between integer harmonics, so the interharmonic current. And we're summing all of this together for all of these samples over a cycle in order to get what we're calling an interharmonic energy, essentially, of that current. And we're going to take this value and we're going to trend it and use that to establish a stable average for the power system. So the nice thing about using this interharmonic energy is we're going to get rid of that DC and those integer harmonics where we expect to see for some of our nonlinear loads the majority of the current on those devices. And so we're going to filter all of that out and just look for the stuff in between those integer harmonics. Now, once we establish a reference and a stable average, and then we're going to look for deviations from that and deviations from a tuning point in order to detect that harmonic signature that is associated with arcing on the power system. And so when we see that arcing, we're going to be able to indicate whether or not there's a high impedance fault in the system. Now, if we look back, and this is once again from another down conductor test. So let's look at this case. We can see once again, if I'm just looking at my current, my measured current at the substation, it's very difficult. And you can see something might be going on here, but it's very difficult to say that this is a high impedance fault or really anything based on this, just looking at this current alone. And for sure, our traditional ground fault protection is not going to be able to pick out this fault due to, especially on a 4-wire multi-grounded system, we're not going to be sensitive enough to detect this fault. However, if we look at this signature from our sum of difference currents, we can clearly see the fault signature. We can see something is happening here. We have our baseline here, and now we start to see some activity. We can clearly see that there is arcing on the system, and we can use this information in order to assert that there's a high impedance fault on the power distribution system. Now, I mentioned tuning a little bit, and this is important. This is an important part of this AST protective element. When we go to set our traditional 50-51 elements, we can, we have a pretty good idea, what's going to be the maximum loading, what's going to be the maximum minimum fault current available. And we have that information available from our power system models in order to set our traditional protection. However, in this case, much of that baseline and what is typical is really going to depend on the load, the type of loading that is on that circuit. And so we probably don't, in most cases, don't have a good feeling of, what is typical interharmonic energy on this particular circuit. So it's important that this element be able to tune to and adapt to the particular circuit where it is applied. And so that is part of what AST does, is actually tunes to the circuit, and it's going to characterize what the typical sum of difference currents that interharmonic energy is going to be for that particular feeder. And then as conditions change, it is going to be able to adapt to those changing conditions in order to adjust and make sure that we are still, our element is still secure. We have changes to the loading. Now, this AST, it is available both in SEL relays, protective relays, and recloser controls. And the nice thing about being able to apply this at multiple locations is that what we see is these high impedance faults, sometimes, remember, we're dealing with currents less than 100 amps. Right? So already we're looking at a small magnitude of fault current, and then we're also picking out the interharmonic energy from that. And so some of these higher frequency components, they are going to be attenuated as they go through the impedance of our power system. So for this example here, where we see a high impedance fault further down the line, we may see this signature at the substation. Whereas if we were closer to the high impedance fault and say 651R recloser control, this is the signature that we might see. And so it's going to allow, being closer to the high impedance fault allows us to be more sensitive and also to be able to detect that fault faster. And so it's definitely recommended in order to increase the sensitivity for high impedance fault detection to deploy this technology at multiple locations within the power system. Now, we talked about AST, we talked about how it works. Now, I don't want to give the impression that this is going to be able to detect 100% of high impedance faults. I'm not aware of a system, a current-based detection system that can detect 100% of high impedance faults on a 4-wire multi-grounded system. In this case, remember, we're using current. We're looking at the harmonic signature of current. In some cases, if we have a conductor laying on, say, dry sand, dry asphalt, we may have little to no current whatsoever. And in that case, we're not going to be able to detect it using AST. And so our sensitivity and our ability to detect fault is going to really depend on what surface our conductor is laying on and how much current we have. What's the available fault current? So it's important to keep that in mind. Another thing to keep in mind when looking to apply AST is that we're detecting arcing faults, we're detecting high impedance faults on the system. Well, not all high impedance faults are necessarily a downed conductor. We can have a case where we have, say, a cracked or a dirty insulator, and we have arcing, a high impedance fault. AST will detect that. If we have, say, a tree branch that is brushing up against the line or making contact with the line when the wind blows in a certain direction, it's an intermittent high impedance fault, and we're going to detect that with AST as well. But if we're sending crews to look for a downed conductor on that line, they may not see anything. So it's important to understand how this technology works in order to understand how best to apply it. So one of the things that we can do in order to give ourselves a higher degree of confidence that a high impedance fault is associated with a downed conductor is we can add another qualifying condition to that. So we can look for an open phase by looking at our sequence components. We can look for an open phase condition based on voltage loss from other downstream IEDs or AMI metering, or we can look for a sudden loss of current. Let's look at a few examples here. So one thing that we can use to look for an open phase is we can look at our sequence components. We can look at our negative sequence current. And so for an open phase condition, we're going to see negative sequence and zero sequence current. And what we can do is we can look for a high magnitude of negative sequence current on the power system. And even better, we can actually look at the ratio of negative to positive sequence current, so that's going to be a percentage of our total loading on the system. Now, one thing to keep in mind is that we need a sufficient amount of load on the conductor, on the phase where we have the conductor break, on that three-phase branch in order to be able to detect this. So if we have large unbalance already, that's going to limit our sensitivity. But also, if we don't have enough load there, then we're not going to be able to detect it. So this method is better for detection of, say an open phase condition on your main line or on a heavily loaded lateral. Another thing we can do is we can use information from wireless FCIs and line sensors in order to look for say a sudden loss of current. So this is the SEL, SLT, FLR fault and load transmitter receiver system. And this is a wireless FCI system that provides both fault indication as well as, that fault data and load data back to a receiver that can go back to SCADA. One of the things that we can detect with this system is a sudden loss of current. So these are shown here on this slide. We can see the different types of events that we can detect. So we can detect, distinguish between a permanent and momentary outage fault. And we can also look at a momentary and permanent loss of current. And so in this case, if we're armed and have normal loading and then suddenly our current drops below this 3 amp threshold, then we have a timer that is set to see whether that is a permanent or a momentary loss of current. And this is a user settable timer here. And then once that expires, if the current has come back, then this was a momentary loss of current, or if the current has still not returned, then it's a permanent loss of current. So we can use that loss of current indication to say, in some cases, to say that we've had, especially comparing to our other phases, to say that we have potentially have an open phase condition. So let's look at an example here. In this case, we have a conductor break. And so we have a conductor break and associated high impedance fault for the conductor laying on the ground on a heavily loaded lateral circuit. And so we are able to detect that arcing associated with the high impedance fault in our 651R. And then we're able, also in the 651R, we are looking at, we have a qualifier to look at the ratio of negative to positive sequence current. And that is, we have a significant amount of negative sequence current in this case because this is a large percentage of our loading. And so then we make a decision to trip that that's most likely a down conductor. And we can provide that information to SCADA so that they can see that we tripped and that there's potentially a down conductor in that location. In this case, we are looking at let's say we have a fault on a relatively lightly loaded tap. In this case, we have a conductor break. We still are detecting the high impedance fault with AST, although we don't have a significant amount of negative sequence current because it's very lightly loaded. However, we do detect a sudden loss of current on a single phase, and this goes back to our SCADA. And so we can either, based on seeing a high impedance fault and one phase with a sudden loss of current, either our SCADA operator can make a decision, or we can have logic running in either in my SCADA logic or in, say, SEL real-time automation controller or something similar to that to indicate that there's a trip and send a trip signal that we should trip because of both of these conditions, and we can send a trip bit to the 651R in order to isolate that circuit. Now, we can combine all of this into an integrated system for detecting down conductors. And there's a lot going on this slide, but we don't have to implement this all at once. The nice thing about building a system is that this has discrete building blocks, and we can build this out as we go. And so it could be that in some cases, and I've worked with many utilities that have just started off piloting AST, maybe at on one circuit in the substation or at a few recloser controls, and that's a perfectly good place to start. One recommendation is, of course, that we're going to want communications, and we'll talk about that here in a little bit more when we get into looking at applications and settings for AST. But we can combine all of this together, and the more communications we have between devices and the more that we can tie all this together, the better the decisions that we can make and the more visibility that we're going to have to what's going on the power system. Now, there is I'm going to talk just briefly about what we call falling conductor detection system. Now, we wrote a paper, we partnered with San Diego Gas and Electric back in 2016 to write a paper about this type of system. And what this does is this is completely separate from AST. This system actually utilizes low latency communication between phasor measurement units to quickly detect a broken conductor and trip the circuit before that conductor hits the ground. Now, the way that this works is essentially we have to have PMU at phasor measurement unit at each end of of the protected line. So think of this as almost like a line differential type of scheme, because what we're doing is we're looking at data measured by both of those PMUs, and we're comparing them and bringing that into centralized logic in order to make a decision. This scheme requires high-speed communication, so we need relatively low latency and high data throughput communication because we're sending a lot of synchrophasor data to a centralized location. And essentially what we do is compare the voltage between the two locations. So we'll look for a sudden change of voltage between PMUs. So DVDT is our primary detection method. We also have some backup methods looking at the negative and zero sequence voltage magnitudes and angles in order to detect this. All of this is sent to a centralized RTAC that's running this logic. It acts as a phasor data concentrator and then runs the centralized logic to detect a break. So one of the challenges with this system is it's very robust, but it requires implementation as a complete system. So this is one of those things that has to be done all at once, and we have to have PMUs at each end of each protected line segment in order for this to be successful. Very interesting application. If you have additional interest in this, I would recommend checking out the paper on the SEL website. Has additional information on this particular scheme. So let's talk a little bit about settings and some application considerations for setting high impedance fault detection, specifically ArcSense technology. So for those of you who have maybe looked at this in the past, or those of you looking at this right now, there's relatively few settings that we'll notice, and it seems, this might be relatively straightforward. Now, when it comes to the settings that are actually associated with AST, what we'll see is they're pretty straightforward and relatively simple. The main thing is, what do we do with this data? And I'm going to talk a little bit about that in this section as well. Let's start off with some of the settings here. Of course, we have an enable. Now, you'll notice we have three options here. So it comes default, if this is available in Aurelia, it comes default set to no, and it will be disabled. We can set enable for this EHIF to yes, to Y, and that will enable high impedance fault detection, or we could set this to T. Now, we talked a little bit about adaptive tuning earlier. One of the important things to understand is that when we enable ArcSense technology, and this is a big application consideration to consider, especially when we're planning to apply this on recloser controls, is we need a certain amount of current in order for AST to tune and in order for it to be armed. So we're going to need to have 5% of whatever our nominal current is in order for AST to function. And why I mentioned recloser controls earlier is in a lot of cases, we may have 1001 CTs in our recloser controls. And so we're going to need 50 amps primary in order to tune and then arm the AST algorithm. And in many cases, if we have concerns about fire mitigation, these reclosers may be in more rural areas which are very lightly loaded. So that's one thing to keep in mind. And in some cases, we may have to look at alternative CT sizing. If you do have questions about that, I definitely encourage you to reach out to your local SEL application engineer to discuss in further detail. Now, when we set EHIF to yes, which is what's recommended for most applications, we're going to, as soon as we have current that is above that 5% of nominal, we're going to start what's called our initial tuning. And so this initial tuning is going to take place over a 24-hour period. And during that 24 hours, AST is not going to be armed. It's not going to be able to detect high impedance faults. What it's going to do is it's going to look at the current and it's going to establish that stable reference that we talked about earlier. And so once we establish that stable reference after the 24-hour period, we're going to arm the element and then go into what's called normal tuning, which allows it to adapt to changes in the loading and changes that it sees in that interharmonic energy, but it will adapt more slowly. So if, say, you just wanted to test the element, that's what we have this T setting for, this test. And so what that does is that will skip the 24-hour tuning period, and that's used for testing purposes only. We don't recommend setting it to T for actual applications out in the field. We have a few other settings here. So we have a setting called HIF mode. And what this does is this actually increases the sensitivity of our high impedance fault detection when this is asserted. So this is just an SEL logic equation that you can set up to say when we should increase sensitivity. I'll talk about that here in the next few slides about ways to apply that. We have HIF ER. This is a SEL logic equation that allows us to trigger a high impedance event report, high impedance fault event report. So this works similarly to your ER equation that's in many SEL relays that you may be familiar with, except this is going to trigger a high impedance fault event report, which is different than our traditional event reports. So our high impedance fault events, and Hardesh is going to go into more detail in a later section. These are going to be not going to include the full oscillography. They're going to be over a span of minutes rather than seconds or cycles. And then we have HIF iTune, and so this SEL logic equation on a rising edge will trigger a a new initial 24-hour initial tuning period. So this is something that allows, if we have, say, a significant change in the configuration of our circuit or the type of loading we have, and we want to initiate manually or automatically initiate a new tuning period, we can do that using this equation. So when would we want to potentially increase sensitivity? We looked at this HIF mode setting, and we talked about having the ability to increase our sensitivity using that. And one of the ways that this can be used is, say we know we have an elevated fire risk. So maybe looking at the weather data, we know we're going to have a red flag day. Potentially, we may want to manually assert that, or maybe we have some automated logic to go ahead and assert, to set a latch to assert our high sensitivity mode for AST. It could be that we want to increase sensitivity after reclosing in such a condition where we have high wind events or storm events. We recently published a paper with PPL on their experience applying high impedance fault detection. And one of the things that they mentioned in the paper with how they use this element, and specifically how they use this HIF mode, is what they noticed is that for many of their down conductor events, especially during storms, they would first see an initial fault that they would trip for using, their traditional fast curves. And then when they reclosed, they would reclose into a high impedance fault and never trip. So essentially the conductor would break, it would hit either the neutral or it would hit something else as it fell to the ground, and they would trip on that first fast curve. And then once it was on the ground, it was a high impedance fault and there wasn't enough current in order to trip any of the curves. So what they did was they increased sensitivity for high impedance fault detection after that first reclose. And so while they were in cycle mode, they increased the sensitivity in some cases. So there's many different ways that we can apply this. Those are just a few examples. If you are looking at, once again, when it comes to setting these elements, if you have questions about, what's typical or what may or may not be a good idea, and you want to reach out to someone, we're happy to talk to you about, how we've seen this applied in the past and what some recommendations are for how to set up these different settings. And at the end of the day, it's really about how we use this data. So here are some high-level considerations when it comes to setting AST elements and how to use that data. We definitely do not recommend just going out there, turning on the element, and putting your HIF fault bits into your trip equation. We recommend setting up the system, going through the initial tuning, and then watching it, seeing what happens. So we definitely recommend applying this in locations where you have communication or easy access to the device that you're applying AST in, and put those high impedance fault bits and alarm bits into your SDR. Bring back those over DNP so that you can see how often they're asserting and if there are any kind of patterns. And whenever you get those assertions, we definitely recommend downloading those high impedance fault event reports and taking a look. And we're more than happy to take a look at those to see what's going on, to see if they look like potential, nuisance trips, or if they look like they're actual high impedance fault events. If possible, it's best to initiate your initial tuning where in the cases where you expect worst case harmonic loading, if possible. And if, once again, we recommend to turn it on and watch it and see if it asserts, see if it asserts, how often the elements assert. And if we see, excessive alarms, excessive fault bits, and, you're able to determine these are definitely not associated with high impedance faults on the system, of course, you can retune or reach out to us, and your SEL, local SEL application engineers is happy to discuss and help out with that. For those alarms, they may intermittently assert, so you want to make sure that if possible, especially once things get set up, that you're going to potentially either latch those in or tie them to an SV with a minimum dropout time, just to make sure that you're seeing those events. And we can, as mentioned before, with that HIF iTune, that's something that can be used as part of, to either manually or automatically initiate a retuning of the system. So we looked at ways to qualify before, with a high impedance fault detection with an potential open phase condition. There are other bits and other methods that we can use to qualify a high impedance fault assertion to give us a higher degree of confidence that it is associated with a down conductor. It just depends on what information you have available. So really, it's going to depend on the specifics of your system, where it's applied, and the different devices and comms that you have available. But once again, we're more than happy to discuss and see what makes the most sense for your system. With that said, we can also, our engineering services group can also provide assistance with deployment of AST, whether that's full system deployment or just helping out for that first pilot. They can help out with developing settings templates or individualized application and testing guides for your organization that fall in with your processes and make sense as far as how to deploy and use AST in the future. They can also be available to assist with testing and commissioning support. So if that's something that you're interested in, please let us know and we can assist there as well. All right, so now I'm going to go ahead and pass the ball over to Hardesh, and he's going to talk about high impedance fault events. And actually, we're going to take a look at some actual high impedance fault events captured in the field.
Anthony, we have a few questions in the chat. Would you be willing to answer a few of those?
Sure, yes, go ahead.
All right, Anthony, the first question we have is, what SEL relays have ArcSense technology?
That's a great question. So ArcSense technology is available in the SEL 751 and the SEL 451 feeder protection relays, as also available in the 651R and 651RA recloser controls.
And Dave asks, is the same algorithm being used in all of those relays that provide that algorithm?
Yeah, that's a great question. So there are actually two different algorithms that run in the 751 and the 451. They run an algorithm based on that interharmonic energy that we looked at, but they also run a separate algorithm that looks at the odd harmonic current. That odd harmonic current algorithm is really more to catch kind of corner case events, but the interharmonic algorithm is what we use for the majority of events. And in the 651R and RA are only running that interharmonic energy algorithm.
Thank you. Another question we have is concerning metering systems that use a power line carrier communications. What is the track record of AST, and should there be any concern?
Yeah, that's a very good question. So if you check out that paper that I mentioned with PPL, it actually talks about some of the challenges that they had with their power line carrier based system, as a TWAX AMR system, and there were some significant challenges there because the way that it transmits on voltage zero crossing essentially looked like a high impedance fault, and we were getting a lot of nuisance assertions. Since then, we have introduced changes to the algorithm to perform cross blocking when we see assertions on all three phases simultaneously, and so that has made the element secure for that particular TWAC system. Now, we have not exhaustively, tested that across all different manufacturers' power line carrier metering systems. However, if you have concerns or you want to take a look at a particular system, we can, we're more than happy to take a look at it and see if we have potential concerns with that particular system for security of the AST element. But in most cases, I would imagine that cross-blocking would help with any security issues associated with power line carrier communication.
Thank you, Anthony.
Hi, good morning. This is Hardesh. Can somebody confirm if you can see my slides?
Yes, it looks great.
Perfect. Thank you. I'm going to continue the presentation of the discussion on high impedance faults. So Anthony talked about how the ArcSense technology works and how it detects a high impedance fault or a down conductor. And then we talked about the settings. Next, I'm going to talk about the high impedance fault events. Like what do the events look like? What information do you get from the events and things like that. And I'm going to talk about one event from an actual field event that we're going to talk about in a little more detail. So similar to the HIS command, so in any SCL relay, if you issue the history command or the HIS command, it gives you a list or a history of all the event records. That's the similar case with high impedance fault detection events. So if you issue the command HIS space HIF, you're going to get a history of all the high impedance fault events. So you can see that it gives you information of what the event number is, what the date is, what the time of the event is, and then it tells you what type of event it is. Is it a HIF fault or is it a HIF alarm? It also tells you which phases were involved in the fault. So you can see that more than one phases can also be involved in a specific fault. It also tells you which group was active at the time of the fault, and it also tells you if it was a downed conductor or not. So in order for the relay to detect or tell you if it was a downed conductor, it needs to see a certain amount of reduction in load. So if there was a certain amount of load and there is a down conductor condition, then you will see a reduction in load. And that's when the relay is going to assert this down conductor saying, yes, I saw a reduction in load. But consider a load or a lateral, a lightly loaded lateral. So if it's a lightly loaded feeder or a lightly loaded lateral, it could be possible that it doesn't have enough load so that the relay detects a loss in load or a reduction in load. So in that case, you might not get this assertion correctly. So in that case, as Anthony mentioned, all HIF faults are not detectable. So what you do is use the integrated approach to look at or use multiple different approaches to detect a down conductor. But again, this gives you a good indication if it's the actual down conductor or not, based on the load reduction. History command is from an actual 751 relay, and a 751 relay saw a high impedance fault. So again, you can see that you get the same information. And here the relay is detecting a high impedance fault on A phase, and you can see that it says it's an actual down conductor. So you get this information from the history command itself. Next, I'm going to talk about actual field event. This is a very interesting event. In this specific event, there are two 651Rs involved. One is the upstream 651R and one is a downstream 651R. The downstream relay is used as a switch mode device. So you can see that the upstream device actually saw a fault current of about 1800 amps, and it tripped the relay, tripped the 651R and went into that reclosing cycle. But as soon as the relay tripped, the downstream relay started seeing this arc. So you can see that once the upstream relay cleared the fault, my fault current went from 800 amps to a very low value. You can see that there is nothing on A and B phases, very, very low amount of current or very low amount of arcing. But you can see that you can see enough arcing on the C phase. C phase has arcing about 200 amps. But again, this amount of fault current is not enough for my 50 and 51 elements to pick up. So my overcurrent and time overcurrent elements cannot pick up because this is not sufficient current for them to trip on this. But as you can see that my high impedance fault bits picked up. So this is my high impedance fault trip on C phase. This is my high impedance fault alarm on C phase. So you can see that the alarm came in a few seconds after the arcing started, or a minute actually after the arcing started, but the trip bit was constantly chattering. So it didn't assert throughout, but it kind of chattered a little bit. So let's see how these bits asserted, the HIF2 and the HIA2. Again, this is for alarming and this is for fault. So what the relay does is, as Anthony explained, that it looks at the SDI, or sum of difference currents. And since we're talking about the fault on C phase, I'm going to look at the sum of difference currents for C phase. So this blue line is the sum of difference currents, or the arcing seen by the relay. This red line is the SDI reference developed by the relay. So the relay compares the reference with the actual SDI. And lastly, there is a margin added for ambient load. So there are changes in the load, right, which can look similar to a high impedance fault. So that's why the relay adds a certain amount of margin to the reference. So based on how much the SDI deviates from the margin, the orange line, over a certain period of time, I'm going to repeat that. Based on how much the SDI quantity deviates from this margin over a certain period of time, the relay integrates or adds these counters. So there is a counter named T7CNTC. So there is a T7 counter and there is a T8 counter. So in this, for the tripping bit, we use the T7 counter. So if the deviation from the margin is very high, you're going to see this counter updating or increasing. But when the deviation starts getting lower, the integrating counter also starts getting a little lower. So what the relay does is it compares this counter value with a threshold inside the relay to assert these bits. And you can see that as soon as the counter is high, this bit asserts. When the counter starts reducing or goes above a certain value, the bit starts dropping out. So this is how the relay detects or asserts this tripping bit for a specific fault. In this case, the SDI the deviation wasn't sufficient enough for the bit to be constantly asserted. That's why you see this chattering bit. All these settings, like how much the counter should increment or what are the thresholds that the counter is compared with, all these settings are calibration settings. So if you're using a 651R, you won't see these settings. These settings are set internally in the relay. So the relay automatically uses these settings to compare the SDI with the reference. But yeah, this is how the tripping bit asserts. Now we've looked at the tripping bit. Let's look at the alarming bit. So this is what the alarming bit looks like, HIA2. So you can see that it's the exact same thing. I have the SDI reference, I have the margin, and I have the actual SDI. So how does the alarming counter assert? The alarming counter also looks at the deviation from the margin, but it looks at smaller values of deviation over a larger amount of time. So it looks at smaller amount of deviation over a larger amount of time. So that's why you see that the counter is constantly increasing for this one. And you can see that the counter value is also sufficiently high. It's not constantly increasing, but kind of increasing gradually. And that's why we see that the alarm bit was constantly asserted for this fault. So this is from an actual field event, and we saw that although the 50-51 elements did not pick up, but the tripping bit and the alarming bit both picked up for this arcing fault. So we have talked about events that we get from a high impedance fault or from the ArcSense technology algorithm. Next, I'm going to talk about reclosing, or why do you want to disable reclosing. So generally, electrical utilities use automatic reclosing to improve service reliability so that you don't have longer outages for momentary faults. But it might be desirable to block or disable reclosing in some cases where you might have high fire danger areas or any areas where wildfire could be a common occurrence. So you might want to dynamically block reclosing in such cases, or you might want to disable reclosing based on what time of the day it is. So there are different strategies that could be used to disable reclosing. You can use manual control, you can use centralized control, or you can use real-time control. We're going to talk or touch briefly on all three of these methods. So again, local control is very straightforward and easy, right? You can enable or disable reclosing by pushing this front panel push button, reclose enabled. So there is a push button on your relay. If you press that, it's going to enable or disable reclosing. But let's say you have multiple reclosers in your system. So it's almost impossible, if not very difficult, to go into all those reclosers and enable and disable reclosing individually. So what is desirable in that case is to have a centralized control. So you can control or disable or enable reclosing to multiple reclosers at the same time. So you should have, not should have, but ideally you should have communication to the reclosers so you can control them from a centralized controller. So for example, let's say you have a bunch of reclosers in a specific area and there is a bad weather in that area, which might result in wildfires. So in that case, you can consider disabling reclosing for all those reclosers in that area. So that's the advantage of having a centralized control over a local control. You can also create logic in the relay. So you can say that enable and disable reclosing only during a specific time of the year or a specific days of the year. So you can use these analog quantities or logic in the relay to enable or disable reclosing only during a particular time of the year. So local and centralized both are good, but in certain cases, we might need dynamic control over reclosing so that I can enable and disable reclosing based on system conditions or where the fault is. So we're going to now talk about how to dynamically control reclosing. So this figure does a good job in explaining what I need and why do I need the dynamic reclosing. So let's think that we have assume we have a 651R, which is protecting this feeder. I have a lateral right here, which is in extreme fire threat area. And I have a second lateral here. Let's assume that this lateral is in an area where there are critical loads, like a hospital or maybe an airport or something. So in that case, if I have a fault on this lateral, ideally I don't want to reclose. I want to lock out immediately. But if the fault is on this lateral, I want to reclose. So now I want to dynamically control the 651R to reclose in certain cases, but not reclose in the others. So what can I use in such a case? I can use these faulted circuit indicators, which are installed on the overhead conductors. So what these faulted circuit indicators do is they can detect the fault and send a signal to a receiver called FR12. So this transmitter is called FT50 and the receiver is called FR12. So once this transmitter sees a fault, it can send the signal to FR12, and then the FR12 can send the signal to 651R, letting it know to either block reclosing or allow reclosing, depending on what area the fault is in. So this is what the FT50 and FR12 looks like. This is my FT50, which is line powered. So as long as you have more than 5 amps of load current on your system, they basically power themselves up. They send the signal to this remote receiver called FR12. The FR12 can be connected to up to 12 transmitters. And this has a certain amount of line of sight range, but if you want to increase the range, then SCL recently come up with a repeater called RP50 repeater. So you can add repeaters if you want to increase the range between the FT50 and FR12. The FT50 takes about 2 milliseconds to detect a fault and send a signal to the receiver. And then the receiver takes about 4 milliseconds to send the signal from the receiver to the 651R. So it uses serial protocol or mirrored bits protocol over serial to send the information, whether this is in a trip state or whether it's in a non-trip state. So it can send a signal over serial to the relay. So it overall adds 6 milliseconds, up to minimum 6 milliseconds to your decision logic. So you can enable or disable reclosing based on that, based on what information you get from the fault transmitter. So again, as I mentioned, that it needs 5 amp of load current to develop a link status between the FR12 and FT50. This should be FT50, sorry. This shouldn't be FLT, my bad. This should be FT50. So yeah, it needs about 5 amp of load information, 5 amp worth of load to develop a link status. And then it constantly keeps sending a link status every 15 seconds to the receiver to let them know that, okay, I'm linked. If the load current is less than 5 amps, it can still detect a fault in such a condition, but it's going to take a little longer for the fault information to reach the receiver than 2 milliseconds that we talked. So if let's say the load is less than 5 amps and you have a fault current which is more than 400 amps, then it could take the transmitter up to 16 milliseconds to send the information to the receiver. So again, you need to have load current above 5 amps for proper or for fast working of the setup. If the load current is greater than 5 amps and you have a fault, then it can send the signal real quick. As I mentioned, it takes about 2 milliseconds to send the signal to the receiver, and then about 4 milliseconds for the signal to be sent to the 651R. So again, if I have a fault on the extreme fire threat area, it means my FT50 hasn't detected a fault. In that case, I'm going to directly lock out. I'm not going to reclose, I'm going to directly lock out. But if the fault is not in the extreme fire threat area, rather if the fault is on the lateral where my important loads are, then I'm going to send this signal, because again, this is going to detect the fault on this lateral, And the FR12 will know that, okay, the fault is on this lateral, which is a critical load, you should reclose. So block reclose on this one, allow reclose on this one. So this is what the dynamic control looks like. So on distribution systems, you can install these FT50 and FR12 devices to allow reclosing in certain cases and block reclosing in others. So this is a handy little tool that can be used along with the 651R to make high impedance fault detection more reliable or to avoid wildfire hazards. So this is the integrated wildfire approach that you can take to minimize the hazards, as Anthony mentioned. So you can see that FLT has been included here and FLR. The RTAC is basically being used as a data aggregator, so collecting data from all the devices. It can also be used for automation and protection or like a centralized control, but here it's being used as a data aggregator. You can see that all these devices that we talked about, FLT, FLRs, FT50, FR12s, and 651R with ASC, all these technologies are used along with each other to build an integrated system. So this brings me to the end of all the solutions that we need to talk about for a distribution system. Next, I'm going to talk about the solutions that are needed or the solutions that are recommended for a transmission system. So the solutions will differ in this case because the ASC can be used in distribution systems, but it cannot be used on transmission systems. So what are some of the solutions? These are the solutions mentioned on this slide. So I can do line monitoring, where basically I try to find what areas of the line the faults are more common. I can also do auto reclose blocking, traveling wave fault location, which is like a very accurate way of detecting the location of the fault. Then you can also use broken conductor detection, which will be added to the 400 series relays. And lastly, synchro wave operations. I'm going to talk about the synchro wave operations, and then Jared is going to talk about the other 4. So we are not going to go into detail of any 5 of them. We're going to briefly touch over them. If you need more information on them, feel free to contact any of us, or there is a bunch of information available on the SCL website as well. But yeah, we're going to briefly talk about all 5 of them. So talking about synchro wave operations, before I jump onto synchro wave operations, let's quickly talk about synchro wave platform. So when I say synchro wave platform, it's a new time series data platform for power system operations and analytics. SCL began working on the new platform in 2017. Part of synchro wave platform are synchro wave event software, this one, which most of you guys are familiar with to look at the event records from the relays. There are also synchro wave monitoring and analytics, which are not part of this presentation. Today, we're going to mostly focus on synchro wave operations. So what is synchro wave operations? Synchro wave operations is a software at enterprise level for utilities. It is a situational awareness software designed for power system operators. The software actually provides situational awareness by integrating GIS location information with high resolution time series data from protection relays or synchrophasers. So again, this software is supposed to complement traditional SCADA and EMS systems. It's not supposed to replace them because it can provide high resolution data which was previously not possible with SCADA and EMS systems. The servers mentioned on the slide bring all the data to the software. The data can be accessed by a web browser by entering the user information. Any data that a relay can provide can be accessed by the software. Currently, this software supports synchrophaser and relay event report data information, but more time series data sources and formats will be added in the future. So this software gives you insight into what your power system information looks like. Now, how does this help you in minimizing fire hazards? Like, how does this help you in reducing wildfire risks? So it can reduce wildfire risks by clearly presenting information to system operators so that can be aware of fire risk areas on the transmission system and respond effectively when transmission events occur. So for example, for fire mitigation, it can allow you to incorporate additional GIS layers, such as public safety power shutoff boundaries or active fire maps. So you can include those fire maps or public safety boundaries within the software itself. So transmission system operators can immediately see where the fires are in relation to your transmission system assets. Synchro wave operation allows operators to drill into real-time data and fault information for any asset being impacted by an active fire. So basically what you do is you have eyes inside your system, so you can look at the system as a whole and get more information on what location of the fire is and how it's impacting your system. So it gives you a picture or information more, which is a higher resolution than previously available with SCADA and EMS systems. So let's look at how this software looks like, or what information does this software provide. So next I'm going to show you a few screen captures from the software itself. So whenever you have any power system conditions or power system anomalies, it gives you a one-click notification. So when you click on this notification, you get all the information. So this is the notification that I'm talking about. So when you click on this notification, you get the source of where this notification is started, and you also get what happened. So you can see that this was my frequency threshold. My frequency went below the threshold, and that's why I got notification. In certain cases, if you have a system event more like a frequency change, operators generally get bombarded by multiple alarms or messages from the SCADA system. This is a better approach to that because you don't get bombarded by a bunch of messages. You get one-click notification, and when you click on notification, you get more information about what's going on in your system. So you can do system-wide monitoring. You can create custom dashboards in this software. So when I say custom dashboards, you can see that a dashboard is created in this one. Here I'm getting all my GIS information. I'm getting my magnitudes. I'm also getting a synchroscope type of a view where I can see all the phasors. I'm getting an oscillographic type of view. I'm also getting a scope view, and I also have bar charts. So depending on what information is useful to me or what information I need to look at in an instant, I can create custom dashboards. And again, these are some of the options available. You can add or modify screens as you desire. Next, again, the software incorporates latest in GIS technology. So you can look at your information from a GIS point of view. Again, you can see that this is my substation. I also have pole coordinates for all my transmission lines. So I can find or locate the problem areas really quick with this software. And again, if I, let's say, get a one-click notification and I'm not sure what the notification is for, or I'm not immediately able to identify what the problem area is or what's causing the alarm, I can actually click on my transmission line or any asset for that matter, and it gives me a bunch of information about that asset. So you can see that once I click on that asset, it's giving me the frequency, it's telling me the voltage, it's telling me the power, the phase angle, and any other information that I desire. So any information that the relay kind of provides me, I can get that same information from this software. And again, it's in real time, it's in high resolution, so you can get much more information from this software and make better decisions or control your system in a better way to reduce the risk of wildfires. This brings me to the end of discussion on synchro-wave operations. Next, I'm going to hand it over to Jared Candelaria so that he can continue with other methods to detect high impedance faults or reduce wildfire hazards in a transmission system. But before I do that, I forgot I need to ask, Regan, are there any questions?
Hi, Hardesh. Yeah, there are a few questions. The first question we have is, what is the required load for the FT50 to start transmitting?
For the FT50, it's 5 amps. So it needs up to 5 amps of load current to develop a link status with the FT50. But it's not like if the load current is less than 5 amps, it's not going to send a fault information. It's still going to send the fault information, but it's just going to take a little longer for the FT50 to transmit that information. But again, the short answer to your question, 5 amps of load current.
Then the other question we had is, can centralized control also switch the relays from group 1 to group 2 as opposed to just stay in the same group as you showed with the FT50s or with centralized control?
Yes, definitely. Yeah. So with centralized control, you can send different status informations to the relay, right? So you need to program the relay. So there are settings in the relay to switch between settings groups. So what you can do is you can program a remote bit, which is sent from the SCADA or from the centralized control, that can actually switch from group 1 to group 2 or from any group to any other group. So yeah, the short answer to your question is yes, you can use the centralized control to switch between settings groups.
Thanks. That was all the questions.
Awesome. Thank you. I'm going to hand it over to Jerry now.
Okay, so we are going to continue on with our discussion on ways to detect broken conductors and mitigate wildfires on transmission lines. So something Anthony already brought up was using the I2 over I1 ratio to detect a broken conductor. And that works pretty good, but the only problem is that we can see here on our sequence networks, this is going to be dependent highly on what our Z0 is. So we can take actually I2, this is looks bad, let me rewrite that. I2 over I1, and we can derive that to be our Z0 total divided by Z0 total plus Z1 total. Now, if we just use the rule, or the rule of thumb, that if we assume that Z0 equals 3Z1, and we can know for a broken conductor that I2 over I1 should equal 3/4 or 0.75. So that's in an ideal condition. However, your zero sequence sources aren't always 100% known, right? And so your zero sequence can change based on the soil resistivity, the moisture in the soil, so that's going to change from over time and throughout the year. Other things that can change are, what are your zero sequence sources? So if you've got, for example, a delta Y transformer in your network, well, that's going to cut off part of your zero sequence network, and that's going to reduce your Z0 total, making this overall number go down. And so as your zero sequence sources change, it makes it more difficult to detect these broken conductors using I2 over I1. Some other issues are, we've got a wide range of I2 over I1, so it can be from 0.1 to 0.8. And this is not going to be unique to just broken conductors. If you've got either an in-zone or out-of-zone fault, you can also see an I2 over I1 ratio similar to this. And it really becomes an issue if you've got an out-of-zone fault and you see an I2 to I1 ratio that's within this range. You do not want to trip, assuming you have a broken conductor or a down conductor, based off of this. So to mitigate that, what we do is we use a time delay. So we time delay our I2 to I1 operation, which that just extends the time that we have an actual broken conductor. Another issue is broken conductors cannot be detected for really lightly loaded lines. So what can happen is if the charging current is comparable to actually the load current, when the conductor breaks, that phase that has seen the broken conductor, it's not going to see a large change in current. So we're not going to see much I2 to I1, and we're not going to be able to detect. The last thing here is we're not going to be able to determine the direction very well, right? So if you have a broken conductor on a certain line, you want to just isolate that line alone. And if you've got a loop system and you've got lines in front and behind you, you don't want to trip those either. So determining where the actual broken conductor is can be difficult using this method. The last thing is if we've got two broken conductors, what will happen is you'll see that I2 is going to equal I1. And so that ratio is going to be equal to 1. And we're not going to be able to detect that condition either. So what we have coming up, as Hardesh mentioned, we're going to have some broken conductor detection that's going to be using charging current only. And so this is going to be available in the 411L in the coming months in the next firmware release. This is going to be added. Currently, none of this is in our relays right now. But we're going to use this new algorithm that is going to be in the 400 series relays, and this is going to be run every 8th cycle. And what this really does is it takes a look at the relationship between the current and the voltage. So how this algorithm is going to work is it's first going to take a look at the phase current magnitude. So this is going to be satisfied when the magnitude of the phase current is less than the charging current for that phase. So for those of you who are familiar with the 411L, we've got charging current compensation that is available for our 87L element. And so we can calculate the charging current that the relay is seeing, or that the line is seeing. The relay can calculate that. So during a broken conductor, the charging current that's going to be measured is going to be up to the break point of the line. And so that should be less than the total charging current of the line. So what we're going to do is we're going to first check, has our phase current magnitude decreased, has our charging current decreased. The next thing we're going to check is for the current of the angle. We're going to do the phase current angle check. So when we've got a broken conductor, again, we're just going to be reading the charging current. So the current should lead the phase voltage by about 90 degrees. So we're going to be looking in this window to see, has our current shifted to be within this window here. The next thing we're going to see is, are we seeing a change in our current angle? The reason we do this is in low conditions, 1 and 2 might be able to be met. So we want to make sure that we're actually seeing a change from load current to this charging current. So that's going to be our third check. And there's just an animation of how we expect the current to look. Let me go back. See, it's kind of moving into this window here. So if all three of those pass, we're gonna run a distance check to see if it's within it's on our line. We're going to calculate the distance to the fault. If all 4 of those pass, we're going to trip. Now, if we get to phase 3 and we do not pass the incremental angle check, we're going to fail, and we're going to issue an alarm to the operator to say, hey, you may have a current imbalance issue, so we're just going to alarm in that case. So that is how the new proposed algorithm works. That's going to be, again, in the 411L in the coming months. Next thing I'm going to talk about is fault location. And so how we're going to attempt to mitigate wildfires using fault location is using the traveling wave, the double-ended traveling, well, I should just say traveling wave fault location algorithms. So what we can do with that is we can pinpoint the fault location within a tower span, and so that we can hopefully, if there is a fault, we can expedite service restoration. We can reduce adder's time. If we've got a damaged insulator, like is shown on this figure here, we can hopefully identify that and replace the insulator. And then also, hopefully, we can prevent recurring faults. Another good thing about this, which we're going to talk about more in detail, is being able to block auto reclosing using this traveling wave technology. So currently, the relays that have traveling wave are the 411L, and that has a double-ended traveling wave fault locator. We've got the T400L, which has also a double-ended traveling wave fault locator. And I believe it also has a single-ended traveling wave fault locator. And then finally, we have the new T401L, which has both the double and single-ended traveling wave fault location. Okay, so when a fault occurs, we're going to have a large step change in voltage. And if voltage is at our peak, we're going to see it go from the peak, so √2 times the phase voltage over √3. So this equation right here is going to be able to tell you what is your change in voltage going to be. So with this large step change in voltage, what happens is we get a traveling wave that is launched from the fault point to the terminals. So we're going to get both current and voltage traveling waves launched from the fault point. Okay, so briefly I'm going to talk about just how the traveling waves work and how we see them in our relay. So I just pulled this whiteboard to have some more room to write. So if we've got this transmission line here, and we've got a fault somewhere on the line, we're going to see traveling waves launched from the fault point to each terminal. And right now I'm just going to talk about the current traveling waves. So we're going to have a relay at each end. And so when we launch these waves, or when the waves are launched from the fault point, they're going to start moving towards each terminal. And notice I've drawn the traveling waves in this diagram in the positive direction. Now when they reach our CTs, they're going to be entering on non-polarity. So what's going to happen on both of these is we're going to see a traveling wave, but it's going to be in the opposite polarity that is seen on the primary system. And that's because we are entering on non-polarity. So anytime you have an internal fault, the current traveling waves are going to be 180 degrees out of phase on the secondary system versus the primary system. And so this is what it's going to look like for an internal fault. And so that is going to be important. Somehow I can't erase these circles. I don't know why. I'll just draw down here. So imagine now we have an external fault. And we have the fault somewhere out here. Again, we're going to have traveling waves launch from the fault point in both directions. But only this one is the one that our relays are going to see. So relay number 1 here is going to see this traveling wave in the same polarity as the primary traveling wave because it's entering on polarity of the CT. So this relay is going to see the traveling wave in the positive direction. Now it's going to travel across the line, and it's going to enter relay number 2. It's going to enter that on the non-polarity side of the CT. So we're going to see this wave in the negative direction. So a good indication that we've gotten an external fault is the waves seen by each relay are in the opposite direction. Now the last thing I'll mention here is what we tell each one of these relays is the time it's going to take the wave to travel across this line here. So this time is the traveling wave line propagation time. So the traveling wave line propagation time. So another good indication of external fault is that we have entered, the wave enters the CT at t equals 0, and we expect it to exit the line, and relay number 2 will see it in the traveling wave line propagation time that we have told the relay. And that's something that you can measure. You can give you a way to calculate it in our manuals, but the best way to do it is to measure it, and we have application guides that show how to measure this traveling wave line propagation time. All right, so with that said, we can go back to the presentation here, and we can take a look at how the double-ended traveling wave fault locator works. All right, so we have this line going from station S to R. There's a fault somewhere on the line. So this point, the fault is closer to terminal S, so we're going to have a wave launch from the fault point to terminal S. And terminal S can calculate the fault location based on the arrival time times the line length divided by the traveling wave line propagation time. Now, wave again is going to be launched from that same fault point to terminal R, and we can calculate the line length minus M. It's going to be equal to the arrival time at terminal R times the line length over the traveling wave line propagation time. So we can solve these equations just for M, and what we're going to find is that M is going to be equal to the line length divided by 2 times the quantity of 1 plus the arrival time at terminal S minus terminal R over our traveling wave line propagation time. So the double-ended traveling wave fault locator method, what it does is it requires communications between both relays. So the relay at terminal S is going to have a high-speed fiber optic channel that's connected to the relay at terminal R. So we're going to exchange data between both relays, the arrival times, and we're going to be able to accurately locate the fault on this line. So let's say you don't have a traveling wave, or you don't have access to, a high-speed fiber connection between the relays, or maybe the relay fiber got cut. Maybe it was because of the fault. We can revert to a single-ended traveling wave fault locator. So if we just look at terminal S here, a wave is going to be launched from the fault point to terminal S at this point T1. Now at this point, what we're going to see when it reaches this terminal, we're going to see some of the wave pass through to the remote bus, and some of it is going to reflect. This is going to reflect to our fault point here. And then when it reaches the fault, it's going to reflect back to our terminal. So we can use this information to calculate the fault point using the single-ended method. So we calculate 2 times M to be equal to time 4 minus time 1 times the line length over the traveling wave line propagation time. And then we just solve for m by dividing both sides by 2. So one thing to notice here is that we've got some other arrival times. All right, we've got T2. This is an arrival time that is before T4. This is a reflection from the remote bus. Right, we've got the traveling wave launch from the fault point, hit our station S, hit this terminal, some pass through to the remote bus, and now some of that wave that hits the remote bus is going to reflect back. So we're going to see that here at S. The other thing you see here is time T3. This is the reflection of the other traveling wave. So we've got a fault, where the wave was first launched from the fault, went to terminal R, and then it reflected from terminal R to the fault point. What we really would see is some reflection here and some of it passing through. So this is the pass-through of that first wave to point T3. Now what the guys of R&D have done is created some high-tech algorithm that's able to discern that this is the first traveling wave and this is the second reflection, and it ignores these two. So what can we do with all of this? Well, we can perform auto reclose cancel, and this is called ARC if you look at any of our bubble diagrams that show all the different functions that are in the relay. And so what you can do is you can say, let's just ignore this underground section for a second. Let's say you've got this just overhead transmission line. And let's say this first part of this transmission line is not in an area that's prone to wildfires. And so if you have a fault in this area, you can allow auto reclosing. Because since the traveling wave fault location is extremely accurate, you can tell the relay, if I have a fault in this first section of line, I'm going to allow my auto reclosing to take place. Now imagine the second section of the line. This goes over an area that may be prone to wildfires. You know, it goes over some wooded areas and some places that may have a lot of dead trees or a lot of pine needles that will ignite. And so what you can do on this section is you can say, okay, if I see a fault happen in this area, I'm not going to allow auto reclosing. As soon as I see a fault in this area that I've deemed prone to wildfires, I'm going to block auto reclosing. So as soon as we trip, we're going to be driven to lockout. We're not going to auto reclose. So that can save us from reigniting the fault and starting a fire. The last section here that's cool is we can also apply this for hybrid lines. And so let's say you have this line and you want to reclose for the overhead sections of the line, but for a fault that's on an underground cable, you can be pretty sure that it's going to be a permanent fault, and you don't want to be reclosing a fault on this underground cable, further damaging the cable. So we can also create a section here for the underground cable to say I don't want to reclose if I detect a fault in the underground section. So how we determine if the fault is on the underground section is we tell the relay some traveling wave line propagation times for each section, and we're going to give it an impedance for each section. And so the actual line is going to look something like this for when we compare our distance to our traveling wave line propagation times. But what we do is we just draw a straight line. So we just draw a homogeneous line between the beginning and end of this hybrid line. So then what we do is when we have a fault, we calculate it on our homogeneous line, and then we project it to our hybrid line. So let's slide here, goes through the steps. So again, we have a fault. Step one is to calculate the fault location M as if the line were homogeneous. Then I'm going to calculate my T prime. So that's going to be what is the time it took for the wave to get there as if the line was homogeneous. I'm going to project that T prime to the non-homogeneous characteristics of the hybrid line, and then we're going to calculate the true fault location M. So this is an example of what our logic will look like if let's say we're just going to be blocking for this underground section, for this underground cable. So we're going to define blocking regions within the relay. And so you can see if the fault location is greater than point M1, and it's also less than point M2, we're going to declare that on the underground section, and we're going to not allow our reclosing relay to reclose for this fault. Now, this can be not only used for underground lines. We can use it for sections, of overhead lines. So you could use that over here on the second part of this overhead line here. So not only for underground lines. But the next thing I'm going to talk about is a line monitor. And so this also uses a double-ended traveling wave technology, and this calculates an event if no trip occurs. So what we found is that we were seeing traveling waves launched before faults occur, and looking at those traveling waves that were launched before faults occurred, we could see that those traveling waves pinpointed where the actual fault occurred. So it was giving us kind of a precursor of what was going on in the system. So what we're going to do is we're going to be listening for these non-fault traveling waves. And then we're going to split up our line into quarter-mile or quarter-kilometer bins, and we're going to count how many traveling wave events we're getting in each one of these bins. And as soon as they get to an alarm set point, we're going to set an alarm, and you can also set another bin to trip. So you could have maybe, if I get 3 alarms in a certain quarter-mile of the line, I'm going to alarm, and let's say if I get 5, I want to be really conservative, so I'm going to trip. And so what we're hoping is this gives us greater insight into the system, and we can actually detect faults, dispatch crews, and prevent faults before they occur. So what we could do is we could dispatch crews, and maybe there's some overgrown vegetation that hasn't been mitigated. So if we're seeing these waves launch, we might be able to get to that location and see, hey, the crews need to go out there and we need to trim trees or cut them down. Hopefully we can detect failing insulators. So like that one we saw on the first slide when we started discussing traveling waves, if we can find a failing insulator before it actually causes a flashover, we can replace it and restore the line. Or if we've just got a dirty insulator, maybe it's just been, there's been some contamination and we just need to clean it off. Last thing is we might be able to gain awareness of where fires are. So maybe this line didn't cause a fire, but there is a fire in the area. Hoping that this, with all the smoke rising up and all the ash in the air, we're going to see these traveling waves launch. They're non-trip traveling waves again. They're just traveling wave events, and we can gain awareness to where these wildfires are at. So this slide shows these precursors that I was discussing. And so what's shown on this slide here is these large traveling waves here on the far right, starting at time equals 0. This was an actual fault that occurred. But before the fault occurred, we saw some traveling wave events happen. And so if we zoom into these traveling waves, we can see that we've got the red trace here. This is from one terminal of the line, and the blue trace is from the other terminal of the line. Now, as I said before, if we've got an internal fault, the traveling waves should be in the same polarity. And so our precursor is showing that we have traveling waves that are in the same direction. And it's not really, the traveling wave line propagation time isn't shown on this slide, but these both arrive in less than our traveling wave line propagation time. You can see that our current here is very low, but we're still calculating a distance to the fault. Now, I don't have the next slide. This came from a larger presentation, but if we look back, so what we're looking at is these 2 precursors here. Now, when the fault occurred, we could also take a look at that, the traveling wave fault location that was determined by the actual fault, and it was found to be pretty close to what we see here, about 14.3 kilometers. And so these precursor waves were able to accurately identify the fault location before the fault actually occurred. And so this feature is available on the T400L and the new T401L. So again, our line is divided into quarter mile or quarter kilometer bins, and we're going to be tracking the events, the precursors that we're seeing at each quarter mile section. So we can see here we've got some bin. This is the true location of the fault. And then the event location here is shown here in these blue squares. And so now we've got these 3 bins here, and we've got 4 traveling wave precursors that were detected. And so what we can do is we can now alarm at this location. So we can tell the crews, hey, we've got a problem here at this section of the line at mile 10. So this is the true location. You should check, a quarter mile behind and a quarter mile above of that fault point. All right, so that's all I have for our transmission line wildfire mitigation. And with that, do we have any questions, Reagan?
Yes, Jared. Which SDL relays have traveling wave fault location?
Yeah, so it's going to be the 411L. That's going to have our double-ended traveling wave fault location. So that's going to require fiber optic communications between the two. And then the T400L and the T401L also have traveling wave fault location. That can be single-ended or double-ended.
Thank you. That is the only question at the moment.
All right. Well, that was all we had. We can stick around a little bit more. If you guys want to answer any questions, if not, we can have Reagan take us home.
Here's a good question. If Anthony is still on the line, can AST be used for a Delta system?
So AST is only for application on solidly grounded power systems. So we can use it on 4-wire multi-grounded systems, or say like a 3-wire unigrounded system, but not on an ungrounded Delta or isolated neutral or impedance grounded system.
Thank you. We have a question, Jared. What are the elements that allow blocking reclosing for portions of a line?
It's just the traveling wave fault location. So the traveling wave fault locator is going to say, the distance of where the fault occurred is X, right? And so if that fault location is determined to be within your blocking zone, then you're going to block. So it's all it is just the fault location.
Thanks, Jared. All right, everybody, thank you. We have now reached the end of the webinar. If your questions were not answered live, you will receive an answer via email. We hope you have enjoyed today's SDL webinar. To learn more about this topic, please visit our website. We hope you will join us for a future SDL webinar. Have a wonderful day.